The possibility of colonization of other planets is a matter that has been on people's minds for many years. In the future, once we can travel through space, we will move forward from one world to the next, inhabiting them with new life along the way and changing these new planets to resemble Earth. Imagine hundreds or even thousands of planets colonized by humans. Life would bloom along the trajectory of our journey through space, and eventually, the galaxy will be filled with beautiful Earths. But how can we achieve a result like that? Just like in any major project, you have to start small. Could you imagine that in the next decade, humanity might start the colonization of our solar system? Today, we're heading to a neighboring planet to find out if life on Mars is possible. The problem, at first glance, the red planet, located only 7 months away from Earth, is completely unsuitable for habitation. On this planet, there are no rivers, no fresh air, no food. The force of gravity on the surface is twice smaller than Earth's, which would have an adverse effect on human health over time. The atmosphere there contains many gases toxic to humans, so an oxygen mask would be a must. A person would not be able to move around the surface without a spacesuit, due to the low atmospheric pressure and constant solar radiation. So how would the first people on Mars and the subsequent colonists survive in such harsh conditions? Oxygen, water. First, let's tackle the matter of oxygen. Scientists have already made significant progress in that direction. In April of 2021, Mars rover Perseverance managed to extract oxygen from the atmosphere, using a tool called MOXIE, by a process known as solid oxide electrolysis. In theory, MOXIE can perform the same function as trees on Earth in the near future. Since this kind of technology already exists, it's just a matter of scaling it up to meet the needs of the future colony. As for water, the vessel that brings the first colonists is expected to be equipped with an efficient system of recycling water, similar to the one on the International Space Station. This creates a little bit of freedom for the astronauts while they search the planet for potential sources of water. We know that in early stages of the development of the solar system, there was water on Mars. Previous expeditions have already found water as part of the mineral and soil composition. Currently, discovered and reliably confirmed volumes of water on Mars are concentrated mainly in the near-surface layer of permafrost, dozens and hundreds of feet thick. The majority of this ice is beneath the planet's surface, since it cannot stay stable in current climate conditions and quickly evaporates once on the surface. The only places cold enough for this ice to remain all year round are the poles, where the ice forms so-called polar caps. In those areas, the overall volume of ice is estimated to be 1.2 million cubic miles. For reference, the sum total of freshwater lakes and rivers on Earth only reaches 24,000 cubic miles. Subglacial lake. If the ice were to melt, it could cover the entire surface of Mars with a 115-foot layer of water. In 2018, after probing the planet, the Mars Reconnaissance Orbiter discovered the presence of a subglacial lake on Mars, 1 mile deep under the ice of the South Polar Cap, about 10 miles in diameter. This became the first known permanent body of water on Mars. In 2021, the ESA satellite ExoMars, capable of peering into the depth of several dozen feet, discovered large deposits of water in the so-called Mars Grand Canyon. Currently, this is by far the most accessible water source on Mars, making the Vales Marineris Canyon network a good place for our first colony on the red planet. Mars Grand Canyon. The supplies from a spaceship won't last forever, so the colony will have to make headway in growing edible crops. Scientists are very optimistic about this process because of the composition of the upper crust of the planet. Martian soil contains many of the nutrients that plants need to grow and survive, such as nitrogen, potassium, and phosphorus. Once we have a stable supply of air, water, and food, we will have built an excellent platform for building a colony from available materials. Martian soil can serve as good material for building shelter, necessary to protect the settlers from solar radiation and dust storms. Of course, the technology most convenient to us would be construction with the use of mega 3D printers. This technique is already being used here on Earth, and it can prove itself quite useful in such harsh and limited conditions as on Mars. Of course, all the necessary provisions and equipment to create favorable living conditions for the first colony will initially have to be delivered by interplanetary spacecraft. SpaceX Starship. But how do we get to this planet? Several projects to create suitable vessels are being developed as we speak. And the SpaceX Starship is currently leading in terms of progress. As of early December of this year, Starship will be launched on its first orbital test flight. The launch vehicle will be super heavy. A notable feature of this rocket is that the rocket itself and the ship are both reusable and can be refueled in Earth's orbit. Once the ship reaches its destination, it can be refueled using the natural resources present on Mars. Water and carbon dioxide, which is very convenient for us. These factors greatly reduce the cost of production and the cost of transporting goods, respectively. The colony will also need a source of electricity to exist. Everything, even the basic things like the extraction of air, water, and food, will need electricity to function. Fortunately, Mars has huge reserves of deuterium. Deuterium, also known as heavy hydrogen, serves as fuel for thermonuclear reactions. Imagine 0.034 fluid ounces of liquid fuel from heavy hydrogen can produce as much energy as 20 tons of coal. All we need to allow us to develop a colony are fusion reactors. Speaking of those reactors, quite recently, U.S. scientists have made a breakthrough in the field of thermonuclear energy. Scientists managed to obtain useful energy in a thermonuclear reaction. But the question remains, can this colony be self-sufficient? There will come a time when Mars will not need Earth to sustain itself. Much like the United States found itself long before the Revolutionary War. Does that mean that life itself will be self-sufficient? No, while we will be able to grow our own food on the planet in greenhouses, what about wild animals? Birds, fish, rivers, oceans? Terraforming, thus in many ways, becomes a necessity. Terraforming is essentially the process of creating another Earth. The general consensus is that terraforming is required for global colonization, and global colonization is required for terraforming. These concepts go hand in hand. So, let's break down the terraforming process into stages that could bring life on Mars much closer to terrestrial life. At stage 0, we, as colonists that arrive here first, can only live in spacesuits with a sufficient supply of oxygen. At this stage, we're faced with problems such as low temperatures down to negative 193 degrees Fahrenheit, an atmosphere full of toxic gases, very low atmospheric pressure which compares to less than 1% of Earth's atmospheric pressure, and of course, the cosmic rays penetrating everything on the surface of Mars. The thing is, Mars has little to no magnetic field, which could protect us from radiation. For reference, a person's exposure to radiation on Earth is 40 times lower. For the next stage, we'll try to get closer to creating conditions where it would be possible to leave the shelter with just the oxygen mask, without the need for a spacesuit. To do this, we need to take care of the radiation, temperature, and density of the atmosphere. Reducing the reflectivity of the Martian surface would allow for a more efficient use of sunlight in terms of heat absorption, which would warm up the planet's atmosphere. This can be achieved by spreading dark-colored dust from Mars' moons Phobos and Deimos, which are among the darkest celestial bodies in the solar system. The alternative is to introduce dark extremophile microbial life forms, such as lichens, algae, and bacteria. This way, the surface would absorb more sunlight, raising the temperature in the atmosphere. If algae or another type of flora took root, it would also introduce a small amount of oxygen into the atmosphere, although not enough for humans to breathe without assistance. Greenhouse effect. In April 2012, scientists reported that the lichen survived and showed remarkable results regarding the adaptive capacity of photosynthetic activity during the 34 days of simulation under Martian conditions at the Mars Simulation Lab. That being said, Mars is already the second darkest planet in the solar system, absorbing over 70% of the incoming sunlight, so there's little scope for further dimming. Another problem with this method is the regular Martian dust storms. They span across the entire planet for several weeks at a time, and not only increase reflectivity, but also block sunlight from reaching the surface. Once the dust settles, it sticks to whatever it touches, effectively obscuring anything previously deposited on the surface from the sun's reach. The terraforming of Mars would entail three major changes interconnected with each other: the creation of a magnetosphere, the creation of an atmosphere, and an increase in temperature. The atmosphere of Mars is relatively thin and has very low surface pressure because its atmosphere is made up mostly of carbon dioxide. When Mars starts to warm up, CO2 can be helpful in keeping the thermal energy near the surface. Moreover, as it warms up, more CO2 from frozen reserves at the planetary poles should be released into the atmosphere, increasing the greenhouse effect. Another way to improve the atmosphere and subsequently create the greenhouse effect is the introduction of ammonia, methane, and other hydrocarbons. Large deposits of ammonia and hydrocarbons have been found frozen on small celestial bodies such as Titan, which orbit the solar system. It may be possible to redirect the orbital movement of these or similar small objects containing large quantities of the aforementioned substances, so they collide with Mars, thereby releasing them into the Martian atmosphere. However, even if we can find a way to prevent its release into space, methane can only exist in the Martian atmosphere for a limited time before it's destroyed. Presumably, this gas will eventually be depleted via the same processes that strip Mars of much of its original atmosphere. But these processes are believed to have taken hundreds of millions of years. Still, well-known compounds that we've been generating on our planet for many years can come to our aid. Particularly potent greenhouse gases such as sulfur hexafluoride, chlorofluorocarbons, or perfluorocarbons have been proposed as initial means of raising the temperature on Mars and maintaining long-term climate stability. These gases create a greenhouse effect thousands of times stronger than CO2. It has been estimated that approximately 0.3 microbars of these gases would need to be injected into the Martian atmosphere to melt the CO2-laden south polar glaciers. This is equivalent to about 3 times the mass of CO2 gases generated on Earth from 1972 to 1992, when their production was prohibited by an international treaty. Maintaining the temperature will require the constant production of such compounds as they're destroyed under the influence of the sun. It's been calculated that the introduction of 170 kilotons of optimal greenhouse compounds annually would be sufficient to maintain the greenhouse effect given the terraformed atmosphere. However, even with all of these efforts, it would be difficult to preserve the atmosphere from erosion by the solar wind due to the lack of a protective global magnetic field. One of the key aspects of terraforming Mars is to preserve the atmosphere, both present and future, from being dispersed into space. Artificial magnetosphere. Some scientists suggest that creating an artificial planet-wide magnetosphere could help solve this problem. According to Japanese scientists from the National Institute of Thermonuclear Sciences, this can be achieved with the use of modern technologies by building a system of cooled latitudinal superconducting rings, each carrying a sufficient amount of direct current. The same report argues that the system's economic impact can be minimized by using it as a planetary energy transmission and storage system at the same time. Also, during the Planetary Science Vision 2050 workshop at the end of February 2017, NASA scientist Jim Green proposed the concept of placing a magnetic dipole field between the planet and the sun to protect it from high-energy solar particles. Imagine a huge magnet located at the Lagrange point L1 at about 320 radii of Mars, creating an artificial magnetosphere mirror. The magnetic field should be comparable to Earth's. This can be achieved with the 1-2 Tesla magnet. Once built and placed in orbit, the shield could allow the planet to partially restore its atmosphere and prevent further evaporation. Let's talk about another monumental structure. Imagine a huge mirror the size of West Virginia made of thin aluminized film. Such mirrors could be placed in orbit around Mars to increase the total exposure it receives. This would direct more sunlight to the planet's surface and could significantly increase the surface temperature of Mars. A mirror with a radius of 77 miles could be positioned as a satellite, using its efficacy as a solar sail to orbit in a stationary position relative to Mars, located near the planetary poles in order to release the CO2 deposits from the ice cap and contribute to the overall warming via the greenhouse effect. At the moment, the main obstacle is the difficult process of launching large mirrors from Earth. And now, finally, thanks to all the aforementioned manipulations, we will reach the final stage. Although the journey to that point is likely to take hundreds of years. By introducing plants, increasing the overall level of oxygen, and creating new biomes on the planet, we'll be able to move around freely and breathe deeply, completely eliminating the need for additional devices that support our life long term. So, what awaits us next, long term? Once production outgrows the consumption needs, these steps will serve as a good basis for the extraction of rare metals such as platinum, gold, silver, and others that are so abundant on Mars. Getting from Mars to Earth is much easier than the other way around. Even more promising is the proximity of the asteroid belt to Mars. Dactyl, a small asteroid moon found in the belt, is 0.8 miles in diameter and is believed to contain more iron than the human race has ever used. These asteroids could be mined relatively near Mars and brought back with little monetary expense. Companies such as TransAstra Corporation and KESE are already planning to mine asteroids. An outpost on Mars would only make things easier. We might see a triangular trade route, much like the one that existed in the 18th century between Britain, the West Indies, and North America. The economic potential is enormous. Each of these steps presents a big challenge, but it's only a matter of time before people set off to conquer Mars. And yet, we can already wonder,